We have five strength parameters which we need to find for a unidirectional lamina. So out of those, what we're going to discuss in this particular segment will be how to find the longitudinal tensile strength of a unidirectional lamina. If you one looks at a typical unidirectional lamina, how we're going to conduct this experiment will be to apply some kind of a uniform displacement to the lamina in direction 1. But what's going to happen is that as we go along the uniform displacement, if we look at the stress strain curve of the matrix, yes, it has a lower Young's modulus typically than the fiber, but you'll find out that the ultimate strain of the matrix will be much higher than the ultimate strain of the fiber. So what we're going to see is that the fiber is going to break first, and that's when we consider that the lamina has failed. Hence, the stress in the matrix when the fiber has failed and hence the lamina has failed will be at this location right here. So if we want to see that how we can use this now in order to be able to find out what the ultimate tensile strength is, the first thing which we have to understand is that the ultimate strain in the fiber will be sigma f ultimate, the ultimate strength of the fiber divided by its Young's modulus. The ultimate strength in the matrix will be the ultimate stress which the matrix can take divided by its Young's modulus. However, what we're going to see here is that it is only going to be able to take this amount of stress which is right there. So if you look at this point here, that amount of stress which is going to take is Em times epsilon F ultimate, because Em is the Young's modulus, and since the strain there is epsilon F ultimate, that will be the amount of stress which will be in the matrix. So we need to include that as our stress which is experienced in the matrix, as opposed to this being the stress in the matrix. So let's go for the derivation here now. So if you look at that, the force in the composite in direction 1 will be the force in the fiber plus the force in the matrix. Now, what is the force in the fiber at when it reaches the ultimate strain in the fiber will be, hey, it'll be the whatever is the ultimate stress in the fiber multiplied by its area. But the amount of stress which is in the matrix at this value of the ultimate strain in the fiber will be this much. It won't be sigma m ultimate because it has not reached to that point, times the area of the matrix, and this one I will call as F1 ultimate. Now what I can do is I can take F1 ultimate divided by the area of the composite, and what the reason why I'm doing that is so that I can write this in terms of the volume fractions. So we know that, hey, this will be the ultimate strength in the direction parallel to the fibers tensile. This will be sigma f ultimate, and if we multiply this by t and multiply this t, this will be the volume fraction of the fibers. If I multiply this by t and multiply this by t, that will give me the volume fraction of the matrix. And if I want to rewrite this in a simpler form, just in terms of the fiber volume fractions, then the formula turns out to be just this one. So that is the mechanics of materials approach to find out what the ultimate longitudinal strength tensile is in the unidirectional lamina. So there's a concept called minimum fiber volume fraction. What does that mean? If you realize that once the fibers are broken, we want to be able to see if the composite can take more load, which means that all the fibers are broken, the fibers are not able to take any more load. So that means that if all the fibers are broken, then the load which can be taken by the matrix will be, or the stress which will be taken by the matrix alone will be of this much. So we want to see that whether this quantity right here is it greater than this quantity? Are there certain volume fractions for which once the fibers are broken that the matrix can continue to take more load? So this should be greater than sigma F ultimate Vf plus epsilon F ultimate Em1 minus Vf. Let's go and see that for what volume fractions is this quantity, which is the matrix taking the load after all the fibers are broken, is greater than the ultimate tensile strength in direction 1. So all I have to do is to just expand it. I'll get sigma ultimate here minus sigma M ultimate Vf here greater than sigma F ultimate here times Vf plus epsilon F ultimate Em plus epsilon F ultimate Em times Vf minus. So if we bring these volume fraction terms together, this one, and this one, and take this to the right hand side and keep this on the right hand side, we'll find out that, hey, the value of Vf min, that's the minimum volume fraction which we need so that the matrix can continue to take the load, is given by this. It'll be given by sigma M ultimate minus Em epsilon F ultimate divided by the quantities which have the Vf in it, which have sigma F ultimate minus Em epsilon F ultimate and plus sigma M ultimate. So if the volume fraction is less than this particular quantity, then what you will find out is that after the fibers are broken, the matrix can still take more load. The other one which we want to talk about is the critical fiber volume fraction. What does that mean? It's quite possible that by adding fibers to the matrix, the composite will have a lower ultimate tensile strength than the matrix itself. So that means that you were not any better off by adding the fibers to it. So in that case, what we call that to be as a critical fiber volume fraction. The reason why we call it critical is that, hey, go ahead and add fibers to the matrix only if it is going to help you to increase its strength. So what that means that this is the formula which we derived for the sigma 1t ultimate. So what that means that sigma m ultimate, hey, what are the volume fractions when the sigma ultimate is m ultimate is greater than this quantity right here. So we do sigma f ultimate Vf here plus epsilon f ultimate Em1 minus Vf. So what we're going to do is we're going to separate out the terms of the volume fraction. Let's go ahead and do that. We have sigma m ultimate here, and we have so if we separate out the terms which have the volume fraction in it and have these terms together which don't have the volume fraction in it, what we'll find out is that Vf critical, that is the volume fraction under which the matrix is going to be stronger than having put the fibers in. That formula turns out to be equal to sigma m ultimate minus Em epsilon f ultimate divided by sigma f ultimate minus Em epsilon f ultimate. So that's going to be the critical volume fraction below which by adding the fibers it's not going to do any good so far as the strength is concerned. So let's go and look at an example of how we can find the ultimate longitudinal tensile strength of a unidirectional lamina. And also the two other concepts which we talked about, the minimum fiber volume fraction and the critical fiber volume fraction. So we're given a glass epoxy lamina, it has 60% fiber volume fraction. The Young's moduli of the glass and epoxy are given to us, whereas the ultimate strengths of the glass fiber and the epoxy are also given to us. So let's go and see how we can do these three problems here. So if we just draw a stress strain diagram, both for the fiber and the matrix. So let's suppose this is the matrix. Then we know that the slope is 3 gigapascals here. And this ultimate strength here is given to us as 70 MPa. What will this number be? It will be the ultimate stress strength of the matrix divided by its Young's modulus. Will be 3 times 10 to the power 9, 3 gigapascals. So that number will be equal to 0.0233. So that number is simply the ultimate strain of the matrix. Now if we look at the fiber goes all the way up to here. It breaks there. We know that the ultimate strength here is 1500 megapascals. So what will be the ultimate strain in the fiber? That's based on this being 70 gigapascals, the Young's modulus of the fiber, 72 gigapascals. So this number right here, let's put it down here, will be epsilon F ultimate will be equal to the ultimate strength of the fiber divided by the Young's modulus of the fiber, and that number turns out to be 0.02083. So this number is 0.02083, and this number here is 0.0233. So you're finding out that the ultimate strain of the matrix is higher than the ultimate strain of the fiber. Let's go and see how we can find out the ultimate strengths now. So part A, we already know what the formula for the ultimate strength in the direction parallel to the fibers is given by this formula right here. So the ultimate strength of the fiber is 1500 megapascals. The volume fraction is given as 0.6. Then the ultimate strain of the fiber is given as this. This is something which we found just recently. And then the Young's modulus is 3 gigapascals. And what is the volume fraction of the matrix? It will be 1 minus 0.6, because 0.6 is the volume fraction of the fiber. So subtract that from 1 gives us the volume fraction of the matrix. And this number here turns out to be 9.250 times 10 to the power 8 pascals, which in megapascal is 925 megapascals. So that gives us the ultimate tensile strength of the unidirectional lamina longitudinal, parallel to the fibers. So let's go and do part B, which talks about finding the minimum fiber volume fraction, which basically means that, hey, what is the minimum fiber volume fraction do we need so that the matrix can continue to take more load after all the fibers are broken. So we already have the formula for it. So let's go and write that down. So since we have that, let's go and substitute these values. The ultimate strength of the matrix is 70 megapascals. Young's modulus of the matrix is 3 gigapascals. Ultimate strain of the fiber is this much. Then we divide by sigma F ultimate, which is 1500 megapascals. that's the ultimate strength of the fiber. The Young's modulus of the matrix is 3 × 10⁹. We already know how much the ultimate strain in the fiber is. Then we add the ultimate strength of the matrix, which is 70 megapascals. And having done this calculation, we calculate our numerator and we calculate our denominator, and this number here turns out to be 0.004980, which is same as saying 0.4980%. So what that means is that if the fiber volume fraction of the fibers is less than 0.5% or 0.498%, then what's going to happen is that the matrix will be able to take more load after the fibers have broken. Let's go and see how we can find out the critical fiber volume fraction. The critical fiber volume fraction, which is part C, we know the formula is given as this. So we know the numbers for all of these terms. The ultimate strength of the matrix is 70 megapascals. Young's modulus of the matrix is 3 gigapascals. The ultimate strain at which the fiber fails is given as this. Sigma F ultimate is 1500 megapascals. Young's modulus of the matrix is 3 gigapascals. And the ultimate strain at which the fiber fails is given by that number. So if we do our calculations, this is what we get in the numerator and this is what we get in the denominator, and this number turns out to be 0.005223, which can be written as 0.5223%. So what this means is that if the fiber volume fraction is less than this number, then what you will find out is that the matrix, it would have been better off, you would have been better off not to put any fibers in it if you wanted to gain any strength in the longitudinal direction. So that's what VF critical stands for. And that is the end of this segment. So let's go and see that how the longitudinal tensile strength test is done. So bottom line is that this particular standard which is used is called the ASTM D3039, and you have 6 to 8 plies, and these are all 0-degree plies, so the fibers are in this direction here, and you can see the gauge length is about 150 millimeters, length is about 230 millimeters, and what you also do is that you put tabs in there. These are aluminum tabs. And the reason why you do that is because you don't want to crush the polymer matrix coupon here. So you put aluminum here so that once it is gripped in a vise, that it stays uncrushed. The tab thickness is about 3 millimeters or so. What we see here is that this specimen is mounted with a strain gauge. You'll have a strain gauge in the direction parallel to the fibers. Then you also have a strain gauge perpendicular to the fibers. This one to measure the longitudinal strain, this one to measure the transverse strain, because then you can find the Poisson's ratio as well. So this is the general setup where you are just simply using a simple uniaxial testing machine. The tensile loads are applied to the specimen at the rate of about maybe half to 1 millimeter per minute, and then what you are doing is that you're taking about maybe 40-50 points for the stress and strain until the specimen fails. So let's look at a graph of a typical test. But before I do that, I'm showing you this YouTube video. I'm not showing it to you within the video, but the link to the video of this ASTM D3039 test is given in the description, so look at it. It's a YouTube video. So these are the results which are available, and you're finding out here with the longitudinal tensile stress being plotted as a function of longitudinal tensile strain. This is measured through the load cell. This is measured through a strain gauge or an extensometer. And from here, if you take the slope of this one, it will give you the Young's modulus in the direction parallel to the fibers. This is the ultimate tensile strength, which is right here. And if you look at the numbers, you can very well see that these numbers are here. That's the ultimate tensile strength. This is the ultimate normal strain which you can apply to the direction parallel to the fibers, and it's from an 8-ply laminate. You also be able to see that there are some modes of failure which take place under longitudinal tensile stress. It's a good idea to see that when you want to conduct this test, three possibilities are there. That you may get a clean break, just like you're seeing right here. You might get some fibers pulling out of the matrix, which is right here, and you might find out that hey, you won't get several breaks, fibers pulling out, matrix breaking, and which is shown right here in real life. And that's the end of this segment.